Hello there. Let's talk about 4.3, which is the expected value of discrete random variables. So to start with, let's recall when we talked about the coin toss experiment and we were looking at x was the number of heads observed. So if we're thinking about the number of heads that we see, but we are tossing two coins. So two coins, and we want to look at the sample space for that. So if I have two coins that I'm tossing, I know that the outcome for the second coin toss is not going to change based on what the first coin toss resulted in. So because of that, I have to list out every possibility for my coin tosses. So when I write my sample space, I'm thinking about all the possibilities for the first coin toss paired with all the possibilities for the second coin toss. So I can think about it using a little chart. I can think for the first coin, I know that I could have a heads or I could have a tails. And that's my first coin. For my second coin, it's still heads, tails, but I can pair it with those first possibilities, the possibilities for the first coin. So it could be either heads or tails. And for my second option here, it could be heads or tails as well. So my second coin is going to be heads or tails, but I need to pair it with the two possibilities for my first coin of heads or tails. So what I end up doing is looking on this chart, and I start with my first possibility, first coin heads, second coin heads. Then I go to first coin heads, second coin tails. Then first coin tails, second coin heads, first coin tails, second coin tails. And those are my four possibilities. So I'm going to write them all out. You just follow your little chart across. Or you can think about it, first coin heads, second coin heads, then I can go to heads, tails, then I can go to tails, heads, and then tails, tails. So I end up with, I marked that one, that was the heads, heads, that's the heads, tails, tails, heads, tails, tails. So that's one way I can make sure I've listed out all my possible sample space. Now from here, I want to look at the probability associated with each value of the random variable x, assuming the two coins are fair. So we're assuming that we don't have a little bit of extra weight from that fat head on Abraham Lincoln there. So then I have four items in my sample space, so if they're all equally likely, then it's 1/4 for each of them. And then what I want to look at is the probability of what are my possibilities for, I was looking for the number of heads observed. So if x is the number of heads, this one will give me 2 heads observed because it was heads, heads. This one will give me 1 heads observed, 1 heads observed, and 0 heads observed. So what I have is these two in the middle. These two sample points are giving me 1 head each. And it doesn't matter at this point which coin it's showing it, but it is 2 different coins each time a different coin is showing the heads. So if I want to know the probability of just getting 1 head showing, then I would add up these two, and that gives me 2/4, which of course reduces to 1/2. So it looks like half the time I should be showing 1 head when I do a coin toss, and 1/4 of the time I should show 2 heads, and 1/4 of the time I should show 2 tails. So that's what my distribution looks like. You can see over here I have it in a table form. So I have x, which was defined to be the number of heads observed, and I have possibilities 0, 1, and 2. That's from right here. There's the 0, there's the 1 twice, and there's the 2. And then the probability of each of those occurring is listed here in the same numbers that we found. So I can say the probability of 0 heads is 1/4. The probability of 1 heads showing is 1/2, and then the probability of 2 heads showing is back to 1/4. So that's what that second column is showing me. And this is a table form way of showing your results, and here's the longhand way. So we can think about the probability distribution for the coin toss experiment as a population distribution. And because of that, we can calculate, because we've looked at all the possibilities for coin tosses, a 2-coin toss, and so that's why we can look at it as a population. And we can calculate the mean, and we call it expected value, and we can calculate the standard deviation similarly to the way we calculate a sample mean and a sample standard deviation. Here are the formulas for them. We're going to go into a little bit more detail here in a minute, but this one is for the population mean, and so we're using the mu symbol. And here's for the variance, and so we're using sigma squared. And here is the standard deviation. So for the population again, so we're using sigma, and it is of course the square root of the variance. Okay, so if I take, let's look down here for a second. We use the term expected value quite frequently when we're talking about probabilities, and it's a mathematical term, not just, oh well, I expected you to come at 3 but you didn't. It's not the same as our English usage of the word expected, but what it means is a random variable might never equal its expected value, but the expected value is the mean of the probability distribution, or a measure of its central tendency. So remember when we talked about flipping coins, you can end up with very, very close to the theoretical probability, which is what we're talking about here. The theoretical probability, or the expected value of a distribution. So in this case, the mean. Think of mu as being the mean value of x in a very large number of repetitions of this experiment. So we take 2 coins, we flip them both, and we mark down the results. And over time, over very, very many samples like this, experiments like this, then we expect the values to occur in the proportions that we show on that previous page. The 1/4 for 2 heads, the 1/2 for 1 head, 1 tail, and the 1/4 for 2 tails. Now, if we look at this chart up here on top, this is showing a sample size of n. So we start with a sample size of 10. That means we did 10 experiments, and the number of times that we had no heads showing was 0.2, or the frequency I should say is 0.2, which means 20% of the time we had no heads showing. Exactly 50% of the time we had 1 head showing, and then 30% of the time we had 2 heads showing. So that's on the ones, it was exactly our expected value, but the other 2 categories for the 0 heads showing and the 2 heads showing is not very close to our theoretical probability. So we show over here the mean and the standard or the sample variance, I'm sorry. And then we come down as we increase the number of experiments, so from 10 to 100 to 1,000, 10,000, 100,000, and finally 1 million coin flips. Then we can look at our expected values, and what we see is that they quickly, in the last 3 iterations there, quickly came very close to 0.25 or 1/4 of the time for having no heads showing. And then same here, we're getting closer and closer till we're really, really close to 0.5 or 50% of the time we have one head showing. And then here on this last one, very close to 0.25 or 1/4 of the time where we're having two heads showing. And you can see then that our mean for that large sample is basically 1.0. So these are all approximately, so I may as well put my approximately sign there. And then the variance is also very close to 0.71. Okay, so we do have those formulas. And for the population mean, we can think of that as just a weighted average. And what I've found is that students don't really understand weighting when it comes to like grades, because many times the teachers won't use true weighting. They'll just say, oh, that test is worth twice a normal test, or it's just on a point system or something like that. So we're not as familiar with a weighted average as we would like to be, but essentially what we're doing is looking at the sum. So that says sum. And then this says multiply each x by its probability. And then we're going to add them. After we do that multiplication by the probability, then we'll add all of them up. And that gives us our expected value or our mean. So we'll take a closer look at that. And remember the population variance, that was the average of the squared distances from x to the population mean. And we don't usually use that formula, but we know that since x is a random variable, the actual outcome from our experiment is a random variable, then the squared distance is also going to be a random variable. And using that same logic, we can calculate the distance by multiplying all of the possible values of that distance by the probability and then summing over all the values. So we end up with something that looks like this formula here. And that's the expected value of the squared distance from the mean, and it's the variance squared. And we find it by taking this. We find all the x squareds, square the x's, then multiply by the probability, then we're going to sum that whole thing, and then finally we're going to subtract off mu squared. And so it's a little bit of a process, but it's not super complicated. Minus the mean squared. And we can do it really quickly with a table. That's our shortcut formula there again. Remember how we like the shortcut formula for the variance? And here's another time where we like that because it's a lot simpler for us to accomplish. So we have one thing to add in here, and that's the standard deviation is, of course, the square root of sigma squared. And that we can do pretty quickly, right? Okay, just like before, we can apply the empirical rule and Chebyshev's rule if we know the shape of the distribution. So it's the same thing. We have to know the shape of the distribution, even when we're talking about probabilities. And so we're looking for these intervals here. This is within 1 standard deviation. This is within 2 standard deviations, and this one is within 3. And so we're saying within 1 standard deviation, it's some number greater than or equal to 0. We don't know if it's an unknown distribution, and it's about 68% if it's following the empirical rule, meaning it has a mound-shaped distribution. For within 2 standard deviations, and you can see this is just mu minus 2 sigma is less than x, which is less than mu plus 2 sigma. Remember, those are the mean plus or minus 2 standard deviations, so that's why I said within 2 standard deviations. Remember, you have 3/4 of your data there if you're talking about Chebyshev's rule, and 95% of your data there if you're talking about the empirical rule. And remember, Chebyshev's is dealing with unknown shapes of distributions like this skewed one. Empirical rule applies only if you know that the shape is mound-shaped. So, and then again, 8/9, this is the same rule as we had before, and 100% within 3 standard deviations. Remember, it was 99.7, so it was very close. And so it's a mound-shaped for that, and this one is for unknown. That would apply for Chebyshev's rule. Okay, so things are not different from before. We're just talking about probabilities this time instead of just straight data from a sample. So let x be a discrete random variable with a probability distribution. So we have the probability for each of the values of x. We know the mean and we know the standard deviation. And then depending on the shape of the probabilities, so if it's mound-shaped or not, we're looking at that shape, then we can look at these probabilities here. And so we're saying the probability that a value of x, some random variable, falls within those 2 probability measures is going to be these percents over here. And let's look at some actual examples. That always helps. So here we have a probability distribution, and we can see our x values on the top row. Those are possible outcomes from our experiments, and the probabilities are shown here. These are what are the likelihoods of getting each of those outcomes from our experiments, and what we want to do is calculate all those things that I just gave you the formulas for. And I really prefer to do these using a table.